Welcome to Washington State University Big Idea Challenge Team's presentation on lead and frost dusting as a novel tool for lunar dust mitigation. I'm Ian Wells, the team lead, and I'm going to start with the challenge. As many of you know, during the Apollo missions, lunar dust was a significant issue. It caused problems with astronaut health, spacesuit equipment, and lunar habitat systems. So, we present the Hyperborea Lunar Dust Mitigation System. It's a liquid cryogen wash with a spray bar for general cleaning and a handheld liquid cryogen sprayer for spot treatment. But how exactly does it work? Well, there's literature on the lead and frost effect and spray cooling. The lead and frost effect is one of the key mechanisms that makes our system work. It occurs when a liquid is far enough above its boiling point that the gas evaporating from it insulates it, and it causes the liquid to move to the lowest point on a surface, in our case, picking up dust along the way. Now, there's no literature on using this for cleaning, making it a ripe area for study. Seeing this potential to investigate the concept, our team began testing. We started with a liquid nitrogen pour. This had higher removal than other dust removal systems. So, we investigated it further with a handheld liquid cryogen sprayer. This proved our concept on a small scale in a terrestrial environment. With high results here, we wanted to move to a more relevant environment, so we tested with a vacuum system. This vacuum system had a single nozzle and showed even higher removal than in a terrestrial environment. With this high removal, we moved towards a scale system with a 1/6 scale astronaut and a spray bar with 4 nozzles. The impact of this testing and of this technology is a concept that, with further development, can be implemented on the lunar surface. It's intended for use at Artemis Base Camp in the foundational surface habitat. However, it should be investigated for other uses as well. And now, our prepared verification demonstration. Enjoy. My name is Ian Wells. I'm the team lead for the NASA Big Idea Challenge team at Washington State University. NASA has identified lunar dust as one of the greatest barriers to future moon exploration, including on the upcoming Artemis missions. The dust is ubiquitous, abrasive, and electrically charged, making it a very difficult substance to deal with. The dust threatens both astronaut health and equipment integrity. The goal of this challenge has been mitigating those negative effects, and specifically, in our case, removing lunar dust in a lunar airlock. Our solution uses a liquid nitrogen or liquid air spray to remove substantial amounts of lunar dust while also pressurizing an airlock. This is in part due to the lead and frost effect. The lead and frost effect is when a liquid is far enough above its boiling point that it actually forms droplets insulated by its own evaporating gas. In our case, these droplets pick up and transport dust from a surface to the lowest point in a lunar airlock. This video is intended to serve as a technology verification demonstration, showing our method and our process. We first discovered liquid nitrogen's use as a cleaning agent by happenstance when we used it to clean the floor after a liquid cryogen demonstration. We noticed the nitrogen droplets moving dust from high to low points and immediately realized that this could be useful for NASA. We tested our concept by pouring nitrogen over a surface and verifying the observed effect, raising our technology readiness level from 2 to 3. Our first challenge was finding a proper lunar dust simulant. Since we're in the Pacific Northwest, we used ash from Mount St. Helens, which has been preserved by Washington State University since the eruption. This ash is very similar to lunar dust, due to its particle size distribution, presence of agglutinates, and composition. Next, we searched for a spacesuit material. After looking through many orthofabric options, we settled on a Kevlar Nomex weave. This is very similar to spacesuit material as verified by microscopy. We began by cutting a section of the Kevlar weave and massing it. We then applied our lunar dust simulant, removed excess, and masked it again to determine the mass of adhered dust particles. For TRL3 liquid nitrogen application, we chose a simple handheld cryotherapy bottle sprayer. After clipping the Kevlar sheet to a board, we remove the dust with a liquid nitrogen spray. After treatment, we masked the Kevlar sheet again to determine the mass of removed dust. This test resulted in over 95% dust removal, giving us the confidence to move to our next test in a vacuum chamber. For the first vacuum test, the liquid nitrogen application method was a single spray nozzle on the inside of the vacuum chamber. For our sample, we used another small portion of dust-treated Kevlar Nomex weave. This vacuum test showed similar dust removal to our localized test, with over 98% of the dust mass being removed. These results bring our technology readiness level from 3 to 4. For our final test, we created a 1/6 scale astronaut suit with the Kevlar Nomex weave. For this test, the liquid nitrogen application method was a spray bar with 4 nozzles, which closely represents our proposed airlock system. During testing, the 1/6 scale astronaut was rotated in place to simulate 360-degree spray coverage. After cleaning in the vacuum chamber, the suit also received spot treatment. Our final test again showed a high degree of dust removal with minimal residual particles found upon post-test inspection. This test raises our technology readiness level from 4 to 5. We set a target removal at 90% of particles less than 10 microns. Our quantitative results meet or exceed this target, and our qualitative results support these findings. As liquid cryogens are certain to be stored in a lunar habitat, the team sees no barriers to future use and therefore presents this concept as a viable solution to the NASA Big Idea Lunar Dust Mitigation Challenge. Further development would focus on improvement of spray nozzles and a larger scale system for testing in reduced gravity. On behalf of the entire Hyperlab team, I'd like to thank NASA for allowing our participation in this challenge. We've learned a great deal in the process, and we are endlessly grateful to be a part of the Artemis generation, putting humans back on the moon to stay. Now, my colleague Camden Butekofer will discuss the first steps of testing.
Our role in ensuring that the health of astronauts and the systems in the lunar habitat are sustained began with the goal to prove that the boiling effect of cryogenic liquids could be harnessed for lunar dust mitigation. To achieve this, we needed to foremost determine the optimum parameters for cleaning with our handheld cryogen sprayer. We then needed to define the parameters for our prototype system, primarily determining our nozzle and spray bar shape, and then testing them on relevant materials in our vacuum chamber. After setting our goals, we used a modified design structure matrix to evaluate the viability of our prototype as we addressed various constraints. For example, we minimized our system through aspects such as decreasing part count, lowering the wash cycle time, and reducing movement required of the astronaut. Additionally, we were able to ensure that our cleaning process is non-toxic and non-flammable. We also found that our method is able to assist in pressurizing the airlock, verifying its ability to work with the current life support systems. Ultimately, a dust disposal system also needs to be designed. We recommend lunar dust to be collected at the lowest point in the airlock so that it can be disposed of through existing disposal technologies. Following these constraints, our final design was a vertical spray bar with additional overhead nozzles and a handheld sprayer for spot treatment. The overhead nozzles, as well as potentially implementing a curtain surrounding the system, could assist in reducing the amount of aerosolized dust in the airlock. Our first steps consisted of preliminary tests of 2 other cleaning methods in order to ensure that our original concept of a liquid cryogen spray was the most efficient. We commenced testing with a compressed air treatment. This was because it would help to replicate the pressurized LN2 gas that would be emitted from our sprayer. However, this method only removed an average of 69.2% of applied dust. We were able to increase this removal to 73.8% through tests conducted with a liquid nitrogen pour. Although still not ideal, we hypothesized that by combining the compressed nitrogen gas with liquid nitrogen, we would be able to achieve even higher removal percentages. This led us to our liquid cryogen sprayer. Our initial tests demonstrated removal of 92% of applied lunar simulant. These and our other preliminary tests verified the hypothesis that a liquid cryogen spray was more effective than other similar cleaning methods. Not only was it more effective, but with our ideal parameters in place, we were able to achieve an average of 97% removal by mass. These parameters, in the order of which they were tested, are as follows. First was the angle of inclination. The angle was measured horizontal to the ground with 0 degrees, indicating when the swatch of fabric was facing the table. The ideal angles were found to be less than or equal to 90 degrees. Next was distance. Using an angle of 90 degrees, we found that the ideal distance for spray application was 40 centimeters. The final parameter was application time. We found the ideal time to be between 20 and 40 seconds. Tests conducted at 30 seconds showed the highest removal with 97%. However, 20 and 40 seconds demonstrated similar removals with 96.5 and 96.7%. The experimental lead, Nathaniel Sweats, will now cover the rest of the testing portion of the experiment.
Now you may be wondering, it works on the Earth, but what about on the Moon? The Moon poses challenges. Specifically, the high vacuum of space will reduce the boiling point of liquids. Our proposed solution suggests that spacesuits can be cleaned in an airlock on return from the lunar surface. To verify this, we needed to design a vacuum system to test the effect of low pressure on Leidenfrost dusting. Preliminary tests were conducted with a single jet of liquid nitrogen at different pressures, and we found high removal even below the triple point of liquid nitrogen. The challenge became to build a working prototype. To do this, we needed to go from a single jet to a spray. We tested cone and flat nozzles and found that flat nozzles had an average removal of 98.4%. Using this data, we were able to estimate that between 2 and 13 kilograms were necessary to wash one spacesuit. Even so, more than 2 spacesuits can be cleaned before full airlock pressurization. High removal in a relevant environment verifies our ability to pressurize airlock with Leidenfrost dusting. We designed a spray bar prototype to clean a 1/6 scale astronaut wearing a mock EVA suit. To do this, we attached 4 flat nozzles vertically for cohesive coverage. Preliminary results showed between 85 and 90% removal on 4x12-inch swatches. Due to boil-off issues in the liquid nitrogen line, there's a clear barrier between vapor and liquid cleaning. While this negatively skewed our data, it helped us understand the cleaning mechanism. With full liquid coverage, we would expect results closer to TRL 3 and 4. Next, we tested our spray bar on the Scale Astronaut. Given the boil-off challenges and our previous findings of higher removal in a vacuum chamber, we decided to test the Scale Astronaut at room pressure. This is so that we could achieve liquid spray out of all 4 nozzles. The same procedure was used as with the vacuum test. The astronaut was cleaned in 10 positions to simulate the rotation of an astronaut, and spot treatment was conducted with a liquid cryogen sprayer. With the boil-off issues addressed, this is a viable strategy for lunar dust mitigation. The concept began as a liquid nitrogen pour, proving that a Leidenfrost effect was viable for future testing. The liquid cryogen sprayer achieved the benchmark of over 90% removal for particles less than 10 microns. To test this in a relevant environment, we designed a vacuum chamber and found an average of 98.4% removal with a single nozzle. Using the spray bar in tandem with the liquid cryogen sprayer, we demonstrated our proposed solution for the spacesuit wash. Greg, take it away.
There are a lot of things that we could test, but the effects of low gravity are more challenging. Using the software StarCCM+, we modeled a liquid nitrogen droplet falling onto a room temperature surface. It was able to bounce and levitate on boil-off gas, as demonstrated in literature and experiment. Lunar gravity caused slower movement and slower boil-off, but apart from that, the droplet still bounced and moved similarly to Earth gravity. To summarize relevancy, we used Mount St. Helens ash as our dust simulant. It's well studied and has similar composition and size to lunar dust. Verification with 2 NASA-approved simulants showed similar performance. Our suit simulant was a black aramid Kevlar, but testing showed similar results with PBI orthofabric and with the NASA-provided suit material. Thank you for that, by the way. Gravity effects were modeled numerically. Droplet movement was similar in Earth and lunar gravity. Airlock pressure will go between a high vacuum and 1 atmosphere. The primary concern with that being nitrogen's triple point at about 12% of an atmosphere, but experiments between 3% and 95% of an atmosphere showed similar performance. As the lunar station's atmosphere will be an air mixture, oxygen and nitrogen, cleaning will likely be done with a liquid air mix instead of liquid nitrogen, but the properties of liquid air and liquid nitrogen are very similar, meaning cleaning should still be effective. And now, here is Lauren Rising on where to go from here.
Before handling and testing with liquid nitrogen, each team member completed a thorough safety training. This included how to properly handle liquid nitrogen, the potential hazards associated with it, and the appropriate emergency procedures. We then completed a risk analysis for each TRL level testing system. For our TRL3 liquid cryogen sprayer testing, we completed a risk matrix, which then informed our safety plan and procedures. For our TRL4 through 5 environmental testing in a vacuum, a hazard and operability study was performed to assess the potential hazards and put in place safeguards to lower the overall risk level of the system. Procedures were then written for TRL4 through 5 in accordance with these safeguards and recommendations. We completed all testing for this project scope and have the following recommendations for further testing. First, we recommend a more detailed investigation of the effect of multiple washes on dust removal and whether this adversely affects spacesuit material. There should also be a further investigation of the precise cleaning mechanisms of liquid nitrogen on the spacesuit. We hypothesize that some of these mechanisms have to do with the vapor, liquid, and gas states of nitrogen, as well as the film boiling and spray cooling effects. The removal of electrically charged dust particles should also be tested. Further exploration of nozzle size, shape, and distance may improve dust removal while narrowing down the operational limits of cryogenic spray cleaning. We also recommend developing a full-size prototype in a large vacuum chamber. When testing, we suggest an HVAC system for moisture control to improve data precision. Finally, we recommend low-gravity testing using hyperbolic aircraft flight on a so-called vomit comet or on a suborbital rocket such as Blue Origin's New Shepard. Overall, there are no significant barriers to implementing liquid cryogen dusting for lunar dust mitigation. Now, Stasha Kulsa will discuss the path to flight.
This technology can be flight-ready by 2026 for the use in the NASA Artemis missions on the Moon. Further testing is needed to investigate the impact of lunar dust on spacesuit materials. It will involve testing that will give us a better understanding of how the liquid cryogen lunar dust mitigation method interacts with spacesuits. After this, low-gravity testing or more extensive CFD modeling is needed, as well as testing with higher vacuum testing facilities that simulate solar wind to further verify scale system results. We recommend investigating other spray bar shapes, especially a curved spray bar. Dust collection systems that will be placed beneath the astronauts during washing should also be investigated. This technology should be investigated for other applications. It could possibly be used on the lunar surface for cleaning the habitat or solar panel substrate surfaces. Having a method for nitrogen liquefaction on the lunar surface will prevent liquid nitrogen from being a consumable of the system. Excluding the handheld liquid cryogen sprayer, all of the system components will need qualification in a full-scale system. After they have been verified, the technology will be ready for testing on an EVA suit terrestrially. Finally, the technology will be ready for implementation in a lunar environment. Now I will talk about our timeline. We were able to adhere to the Big Idea Challenge timeline, which was our first objective. Objective 2, the experimental measurements of dust removal efficacy from simulated spacesuit materials with liquid nitrogen, were completed for the most part before our goal deadlines. Objective 3, the computational modeling of the lunar dust removal measurements to determine the optimal spray angle and impingement velocity, was completed, though it was not by our initial goal. The demonstration of a 1/6 scale prototype of the Hyperborea dust mitigation system with a model EVA suit covered in regolith simulant was completed on time. This was our fourth objective. Now, John Bussey will tell you about our budget.
Our $124,000 award was efficiently spent primarily on parts and equipment for testing, a professional verification demonstration video in lieu of in-person travel, and student wages, mainly to carry out our 592 trials. We present a promising new technology to assist lunar missions by efficiently cleaning spacesuits. This system has many benefits, including simultaneous pressurization of a habitat airlock, no toxicity and flammability, low material and power requirements, and a simple path to flight. With these benefits and very high removal, this system can be implemented on the Moon. This high removal was verified with robust testing on simulated lunar dust and spacesuit fabrics. Elevating through TRLs, we removed up to 98% of particles in a relevant environment and over 90% of particles less than 10 microns. This system was elevated to TRL 5 by qualitative assessment of a 1/6 scale astronaut. We additionally present recommendations for system parameters, future improvements, and implementation strategies. With these refinements, this system will become even better and ready for the Moon. Through our work, we believe that this technology is viable for use by 2026 to support the NASA Artemis mission of returning the United States to the Moon to stay. The Hyperborea team here on the right would like to thank our many collaborators. We greatly appreciate the help of our industrial partners, Smart Materials Solutions, and PBI Performance Products. We also are indebted to our university partners, Dr. Konstantin Matvee's laboratory and Dr. John McCoy's Institute for Materials Research. Their support of our work was extremely useful and ensured successful completion of this project. Finally, Dr. Jake Leachman's HyperLab was instrumental in making this project happen through their assistance, support, and feedback. Finally, we would like to thank our funders, NASA, the Big Idea Challenge, and the National Institute for Aerospace for funding our discoveries and innovations. Thank you.